So let's talk about two reducing agents for alcohol, aldehydes, and ketones within the context of what they can do. And these two compounds are going to be sodium borohydride, NBH, and lithium aluminum hydride, LAH. Now, lithium aluminum hydride actually for me has a great personal connection. I have a friend with the initials LAH, and so it was kind of great in college. Like even she was proud of the fact that her initials matched up with this compound we're working with. So what is lithium aluminum hydride? Lithium aluminum hydride. Well, LiAlH4 is a metal hydride. In the case of metal hydrides, these contain hydrogens with a -1 charge. So these hydrogens here are very motivated to give their electrons up to they're very motivated to reduce compounds. Now, lithium aluminum hydride here is a very aggressive reducing agent. So if we have any type of aldehyde or ketone, and hit it with LiAlH4. And specifically, we're going to have to do this in a polar aprotic solvent. So the reason we need to work with a polar here is because this is a salt, we want to dissolve, but we need an apolar because this is going to react, if we have any H pluses in solution, they're going to react with the H minus here to give us H2 gas. So after we do this reaction, we're going to do a subsequent acid workup. And this will convert any aldehyde or ketone into an alcohol. Now, a brief comment on this. This carbonyl here is trigonal-planar, and the LiLH is going to add hydrogens to both sides. So if we end up producing a chiral center when we form this alcohol, we are going to end up forming both R and S alcohols in a racemic mixture. Now, the issue with LiLH is that it is super aggressive. So not only will it do this reaction with aldehydes and ketones, if we have a carboxylic acid, LAH, will also reduce this to an alcohol in water. If we have an ester, we will produce we'll produce two different alcohols. If we have a nitrile group, got no space here, yeah, RCN, this will produce the amine. In the case of epoxides, what it will do is actually open up the epoxide ring and put the alcohol on the more substituted carbon. So LAH here is a very aggressive reducing agent. It's hard to find things that it won't reduce. But let's say you come across a scenario where you have a carboxylic acid on one side of the molecule and an aldehyde or ketone on the other, and you only want to convert the ketone or the aldehyde to an alcohol. Well, this is where sodium borohydride is going to come in. So NaBH4. Now, this is also a hydride, but it's a much less reactive hydride. So we're still going to work with our hydride, and in the second step we're going to acidify NaBH4. But here, these are going to be the only two reactions that sodium borohydride is going to perform. It's not going to reduce an ester, it's not going to reduce a carboxylic acid, and it's definitely not going to reduce something like a cyano group. So these are your two options. Lithium aluminum hydride is going to reduce everything down to an alcohol, whereas sodium borohydride can only do this with aldehydes and ketones. Now, also practically, sodium borohydride is a bit easier to work with. It's not going to be as sensitive to any type of water contaminations, but it is still sensitive to water and is still sensitive to a protic solvent, so you are going to limit yourself to a polar aprotic solvent. But these are your two options here, sodium borohydride and lithium borohydride for reducing ketones and aldehydes and alcohols. But with the LAH, lithium aluminum hydride, you've also got more additional synthetic options at your disposal.